始めたいと思います。間違ってるな、これ。10ハード16。間違ってた。直しました。ここにテキストあります。で、ここでダウンロードできます。それから、だいたい30ページかな。で、30ページで、トムソン効果が終わったので、次はヘリコンウェーブ。4番のヘリコンウェーブいきたいと思います。Suppose that a metal is placed in a uniform magnetic field H. Along the z-axis, let an AC electric field E times exponential minus I omega t be applied perpendicular to H. If the electric Part A, if the electric field is circularly polarized, which is EY equal plus minus IEX, show that equation 1.28 must be generalized to something. What is 1.28? 1.28. And this one, J omega, sigma omega, E omega. I can write this maybe. Whiteboard Fox, this one. I can write J omega is sigma omega E omega. Is this correct? Let me see. E omega, J omega. So the funny point is this is proportional. E omega. Sigma can be complex. So this is very interesting. This and this is complex vector. This is a complex number. Complex. Then, so this is kind of funny. The question is J parallel to E? My naive question. Is J parallel to E? And I don't know, because these are complex numbers. Anyway, so then I can go to page 30. This is generalized. Circularly polarized. Show that equation 28 must be generalized to this. field. I have to go back. Then sigma omega is sigma 0 divided by 1 minus I omega. Is this the case? I omega tau. Okay, so then I can go to page 30. Omega C. Why do this is complicated. Okay, let me see the solutions. I go to solution. .4. Is it 1.4 or 1.5? 1.4. So this is the equation of motion, kind of. H is perpendicular to H. E, T equal real part of E omega. Okay. Seek steady state solution of this form. P omega I omega P omega is something like this. H is constant. So we can solve. This way. You can obtain this way. The solution looks like this, where omega c is like this. The current density is like this, where see, I think the important thing is to understand what's going on. Because now the situation is like this. You have, this is H. Magnetic field is vertical direction. And electric field is kind of strange. Electric field is perpendicular. Let the AC field be applied perpendicular to H. uncircularly polarized E. How do you describe a circularly polarized E? It seems like, okay, E absolute value it seems that this electric field looks like this. Maybe I change color. Electric field is red. This electric field rotate. With omega, angular frequency omega. Then AC electric field, if the electric field is circularly polarized, show that, then what is the J? It's very hard to understand what's going on with this solution. It's very very difficult. What's the solution? I think I kind of understand. See, this one, if you have this, if you have only H, yeah, so electron experience some spiral motion like this. Then this angular frequency is omega c. Okay, so then if your electric field, is like rotating same direction, in the same direction, if your electric field is rotating in the same direction as this helical circular motion with the same angular frequency, then this will be double, I think. So this one plus omega, double. But if your circular electric field is circulating in opposite direction than the helical motion, you obtain omega c. Omega c is actually cancelled by omega. So in this extreme case, you can see the denominator here. If this omega tau part become either twice or zero. If omega equal omega c, this part becomes 0 or 2 omega. Double frequency. It's complicated. Then next one. Show that in conjunction with 161, Maxwell's equation 131 have a solution exponential e sub x is e0 exponential I kg minus omega t. E sub y is plus minus I x, and E sub z equals 0. Provided that k square c square is epsilon omega square, where epsilon omega is 1 minus plasma frequency square divided by omega times 1 over omega minus plus omega c plus I omega tau. Sketch epsilon omega for omega larger than 0, choosing the polarization EY equal IEX, and demonstrate that solutions to k square c square equal epsilon omega square exist for arbitrary k at frequencies omega larger than omega p and omega smaller than omega c. Assume the high field condition omega c tau, which is larger than 1, much larger than 1, and note that even for hundreds of kilogauss. Omega p divided by omega c is much larger than 1. Part D. Show that when omega much smaller than omega c, the relation between k and omega for the low frequency solution is omega equal omega c. Is this my highlighting? Omega equal omega c bracket k square c square divided by omega p square. This low frequency wave, known as a helicon, has been observed in many metals. Estimate the helicon frequency if the wave is 1 centimeter and field is 10 kilogauss at typical metallic densities. Some paper. It's kind of a difficult question. From Maxwell equation, you obtain this. What is a K in this case? K. Sketch plot. I think I would say this is some more specialized topic, and I don't know if we should learn this in this context. Let me try the other solution. There's the other solution to exercise. Was it solution to exercise? Okay, anyway. This is different solution. Do you have a solution? Was it here? I think this one. So number 4, 2 solutions. Let's see the first one. This seems same. This is same solution. .1 hertz. This is different. So let's see the other one. This is 1.3. This is 1.4. This looks a little better, I would say. Anyway, let me see. How should I treat this? I think I need more explanation about electromagnetism to understand this part. Helicon waves. So I'd probably like to skip this program, and then next time I will work on problem 5.